Well, thanks for organizing this. This is really nice. So I used to sit here. I used to work with Guillermo Sapiro, so I have a background in computer science and math, but now I'm a faculty in the med school in radiology. So a lot of what I'm going to talk about here is more applied. And so Hamza also used to sit here. He graduated from EC and he knows a lot more about the details. So during the discussion, I think we'll all chime in. So um, you're going to see, so this is great because you're going to see this actually fits really well with the last few talks. What we are trying to do, so we do MRI, and I do something called diffusion MRI, not diffusion models, diffusion to look at diffusion of water molecules in the brain, because it teaches us about how the brain is connected, how the axons run through the brain. One big question is driven by, you don't need to look at details, but things like this. So this is the way, based on some of the parameters that we can plug into the MRI machine, the diffusion signal will look like, depending on the orientation and of axons and their size. So it's an optimal design problem as well, but the problem here is that there's another kind of layer where we need to learn the space of parameters to tell the machine how to acquire the data so that they can then best fit some biophysical models that rely on these kind of atoms. So we have some basic, diffusion in a cylinder, diffusion in a sphere, and we plug all of these into a model that will describe the data. And so up until now, there was very little work on this. And so we use something that you probably are very familiar with, differentiable programming. I'm not going to go through this, but this is something that has been extensively used in deep learning and robotics because it gives us a way to compute derivative of ugly functions like this without actually having to do it by hand. And this is just one example. Most of these models are actually combination of various compartments. So think of this as diffusion within axons, so in the brain, diffusion outside the axons, and diffusion in fluid in the brain. So if you plug all of these models that I was showing together, you can build pretty much any model you want. We're interested in that. But to be able to do this, we need to be able to program the machine so that we get the best information to fit the best model and get the best parameters. And so this is where this framework using automatic differentiation and optimization comes in. And so basically the output of this is a list of parameters for a given model of diffusion in the brain that we can then go and try on the MRI machine. And so that's one thing we're working on. And then the other aspect is kind of a more straightforward application of generative AI, in this case, ESR GANs, where we have this project, a brain initiative project, where we're collecting data. These are in vivo data. These are ex vivo microscopy type of data, optical coherence tomography. You can see there's a factor about 100 in terms of their resolution. So we'd like to get to something like this, but just with this. And so this is, again, very straightforward, but Hamza and I should have said, Hamza worked on this part a lot. And then he also worked with Pramod on this aspect, on the computational aspect. And this is the team this is, petabytes of data, MRI and OCT. So it's a lot of data. What we're trying to do is to learn a mapping between the diffusion MRI data that's relatively easy to acquire and the really high resolution data to generate something that will be more informative than the raw low resolution data. And so that's done using, like I said, super resolution generative network. The modification here was, to enhance, some of the layers for high resolution, and then we just do some transfer learning on a pre-trained version of that. And that gives us more detailed information. And, you may not know what this is, but I can tell you there's a little more information here, and it's actually quite useful because we can get, quick data and get more information. So this is, I'll stop here. 2 examples of things we're working on, and then in the discussion, we're getting more into multi-layer interconnected graphs to model this kind of brain data. And so there's a lot of network science theory that we've been looking into that would be also another avenue for collaboration. So that's it. Yeah.
In this domain, of course, you're sort of saying that AI could help, right? But isn't there also an opportunity, because when you're doing an MRI of a particular organ, right? you know something about the geometry of that organ, you know something, you know.
So to model it more explicitly.
So the question is, super resolution, you know, in computer vision, you give me a lot of images, combinations of high resolution, low resolution combinations, and learn the mapping.
We don't have a lot of images. That's
No. That's
Okay.
like, if you have a lot of images, you could do that, right?
Right.
If you don't have a lot of images, but if you knew the model of the face, you could probably do much better job of super resolution with a small number of images.
Yeah, we don't, you
So
know.
something similar here, because you don't have a lot of images, you need even more, you need the model even more.
Yeah.
So the question is, and I guess to you and also the people here in the audience who are working on related problems, is there an opportunity for us to bring these people together? I mean, University of Minnesota is one of the hotbeds of.
Approach. The knowledge guided.
Yeah,
Yeah,
I mean,
yeah.
and also this is the place where you have a lot of the MRI data. I mean, you have some of the biggest magnets here.
Yeah,
Just
yeah.
a couple of blocks away.
Yeah, they're just down my office.
It's the world class facility. I think the number one is in the world.
If you have the biggest magnets in the world, why don't you have enough data?
Oh,
So it's not necessarily about the size. It gives us really high resolution data. They're obviously much more difficult to acquire. It took about 10 years to get to between the delivery and so this is actually acquired with this 10.5 Tesla.
So the idea would be that not everybody else can have the high resolution magnet that the University of Minnesota has.
Yeah.
So
I should say there is one that's slightly more powerful in France. So it's the strongest in the US, but just to be fair.
The high resolution images, and if you can go there from the coarse images, then people with smaller magnets could take the image and then get here.
Right.
And there are small number of images, but if you learn the mapping with the models, like it's digital. I mean, again, I'm almost saying.
No, that's exactly what we're thinking about. You know, you can generate, you know, you can maybe replace that, which is ex vivo. You need to slice the brain by something high res with a unique system like what we have here or you know, or somewhere else, and then learn from that to be able to apply this to any clinical scan. That's the, you know, idea behind it.
And some of you are working, I guess.
Yeah. But you know what, I think one of the challenges here is really, you know, because MRIs are 3D data. So it's super expensive. I mean, it's hard to acquire enough data, and also it's expensive to compute because you want to put that on the GPU, you need many GPUs. Because it's a 3D volume.
That's true, but then the advancing the frontier is even more important. How do you bring
Yeah,
it
but
down,
the
right?
method I talk about, yes, definitely is there.
There's a lot of room for there's a lot of room
Yeah.
for improvement in terms of, you know.
So all these are actually US problems. Like they don't think and
Yeah.
It's
These
a
are-
standard US problem.
So what I'm saying, this is an area where we have the world-class expertise or world-class data sets, right? We need to develop these combinations where we sort of say, look, we have, these are unique images, nobody else can have these, right?
Yeah.
And the expertise, I'm sure, in your.
Yeah, and this was, you know, absolutely, I agree. And this was more of a feasibility to say, okay, does it actually do something reasonable? And then I'm sure that there are many other ways to do it better. But this is actually, yeah, an interesting application.
And maybe there are other people, there are quite a few people who work
Yeah.
in the College of Science and Engineering.
You know, Mohammed, not here today, right? ECE. So yeah, he's definitely an expert also. You go down.
Next door.
Yeah.
I say.
He's in the same room.
Who are you talking about?
Question.
Oh, Mehmet, yeah.
I was with GE Research for a while during the pandemic. And as part of that, I was reaching out to small companies with enhanced image processing.
Mhm.
And someone came to us with some medical enhanced image processing. They finding very good success in radar image processing
Okay.
using these techniques. If you want, I'll share your name, but they may have some. I left GE. I know it didn't move in that direction, but there may be. They seem to be have some techniques for enhancing the image. Now, it's very much for a human, but if you want, I'll pass your name on to them because they're just a startup and they're hungry. And they had some technology that came out with, I think, some old research image processing a while back from Boeing or something. But,
Okay. Yeah, sure. That'd be interesting.
I'll get your name.
Sure, yeah, you can. Thank you.
One small question. Oh, go ahead, please.
I have a question from very domain perspective.
Yeah.
So the images that you showed me, are there MRI images of normal organs? Or have you considered cancerous kind of, because MRIs are often used for cancers.
Yeah.
So when you're transferring a low resolution image to a high resolution image,
Yeah.
these lesions that radiologists look for could or could not be enhanced synthetically, right?
Yeah.
So my question is, how are you validating the correctness of your image enhancement?
Yeah, we haven't.
Yeah.
So we have not.
Right,
But that's a good
we
point.
use an analogy here, right? So in climate and all, we talk about downscaling. Right, which is, so you may have a global climate model and I want to get a more detailed regional model. And yeah, and we often use a lot of correlates,
Okay.
right? I don't know if it's similar, is this a similar downscaling problem or am I going too far here?
The correlate will not be there.
Correlates may not be there.
Yeah.
No, but they may
What would be the
because
correlate for
EHR
climate?
You have EHR records, right?
I see.
So you
But
might,
are you correlating those information in order to get this high resolution image is my question.
or should you?
Oh, yeah, should you?
What do you think?
Well, we could, I mean, if we learn from, we could learn from examples that include this type of pathology, then yes, of course. But no, here this is purely
Yeah, so if,
a demonstration.
okay, so the question was, have you considered those images which had lesions of cancer?
No.
Okay.
Sounds like a project.
Thank you.